Let's summarize substituent behavior, which we've seen over the course of several videos. The behavior and trends that we have discussed are summarized in one diagram seen on this slide, and these categorizations apply to the vast majority of cases. Let's take a moment to walk through this diagram. On the left-hand side of the diagram, we see activating groups. Now, activating groups can be further subdivided into those that are weakly activating, moderately activating, and strongly activating. The further we move to the left, the more reactive the compound will be toward EAS reaction. So what makes a ring weakly activated, moderately activated, or strongly activated? Well, we see those descriptions underneath the arrows. Inductive donation of electron density leads to weak activation of the ring. And this happens when alkyl groups are substituents on the ring. On the other hand, moderately activated rings result from resonance donation into the ring, but also into another group. So for instance, when the benzene ring is connected to the sp3 oxygen of an ester, that oxygen's lone pair electrons may be delocalized into the ring and into the carbonyl. So the oxygen donates electron density to the ring, but not as forcefully as it would if the carbonyl were absent. Strongly activated rings result from substituents that can donate electron density through resonance into the ring only. An example of this would be an amino group. On the right-hand side of this diagram, in green, we see deactivating groups. Once again, these can be broken down into weakly, moderately, and strongly deactivating. As we move further to the right, the ring becomes less and less reactive. Weakly deactivating rings result from inductive withdrawal of electron density, such as what we see with the halogens. Now, this is a good point to pause and look at the bottommost labels, which relate to directing effects. All activated rings, as well as weakly deactivated rings, experience orthopara direction. As we move into the moderately and strongly deactivated rings, those will experience metadirection. Moderately deactivated rings experience withdrawal of electron density through resonance. An example of this would happen with a ketone being a substituent on the ring. Strongly deactivated rings have withdrawal of electron density by resonance and induction, or by the inductive withdrawal caused by a cation. Examples of this category would include a nitro group as a substituent, or a quaternary amino group as a substituent. There are some Friedel-Crafts reactions that are problematic. These are reactions that will fail, and they should therefore be avoided when designing synthesis. Friedel-Crafts reactions, be they alkylation or acylation reactions, do not work with rings bearing nitro or amino groups. Nitro groups withdraw a great deal of electron density from the aromatic ring. They simply make it too weak of a nucleophile for these electronically demanding reactions. So nitrobenzene will not successfully undergo a Friedel-Crafts alkylation or a Friedel-Crafts acylation. Amino groups are also problematic in regard to Friedel-Crafts reactions. Amino groups are Lewis bases, so they will react with the aluminum trichloride that is utilized in a Friedel-Crafts alkylation or acylation. The resultant Lewis acid-base complex also results in an electron-poor ring. And this is because of the powerful electron withdrawal through induction by the positively charged nitrogen. The intensely electron deficient ring that results is too weak of a nucleophile for Friedel-Crafts reactions. Friedel-Crafts reactions are also problematic with rings bearing carbonyls conjugated to the ring. So for example, if we have an aldehyde, ketone, acid, amide, or ester attached to the ring, and an important distinction here is that the connection in these cases is from the ring to the carbonyl carbon. Similar groups, such as the nitrile, also lead to problems. And the reason is, for all of these cases, aluminum trichloride complexes with the lone pairs of these functional groups, much like we saw on the preceding slide. The resultant Lewis acid-base complex renders the aromatic ring too electron poor to react in a Friedel-Crafts reaction specifically. Now let's examine EAS reactions of di-substituted benzene rings. In some instances, the two substituents will both direct EAS reaction to the same location. These are the easier cases because we have no decision to make. We simply follow the directing trends that we have learned thus far. The chlorination of para-nitrotoluene provides a convenient example. The methyl group is an activating ortho-para director, while the nitro group is a deactivating meta-director. The methyl group directs only ortho to itself because the para position is already occupied. And this activated site is the same one that is meta to the nitro group. Therefore, the position at which a subsequent EAS reaction will take place is evident. And I should also note here that because of the symmetry of the molecule, it does not matter whether the chlorine is placed on the left-hand or right-hand side of the methyl group. Those two products would in fact be the same molecule. Some substituent patterns require us to make a choice, though. These are more difficult cases. And an example of this situation is provided by the chlorination of meta-nitrotoluene, an isomer of the compound that we considered previously. The methyl group directs ortho and para to itself, the positions shown in red on our diagram, while the nitro group directs to the only unoccupied meta position relative to itself. In this instance, it seems that every location on the ring that is not already occupied could be a candidate for reaction. However, we can quickly and easily narrow the choices using two simple guidelines. The first is that it is the most activating group on the ring that controls the regiochemistry of EAS reaction. The most activating group is all that matters. The second guideline is that substitution does not occur between two substituents on the ring for steric reasons. Keeping these guidelines in mind, let's re-examine the chlorination of meta-nitro-toluene. The methyl group is activating, and the nitro group is deactivating. So by our first guideline, the methyl group will dictate the course of the EAS reaction since it is the most activating group on the ring. We know that it directs ortho and para to itself. However, we must disregard the site between the methyl and nitro groups because it is too sterically hindered for reaction. This leaves us with two viable sites for EAS reaction to occur. Since they are relatively similar to one another from a steric standpoint, we obtain a mixture of regioisomers from this reaction. In other words, we have two products where the chlorine has been placed in both of the positions where the methyl group directed. The same principles apply to predicting the products of EAS reaction using polysubstituted rings. In this situation, we have a tri-substituted ring where the substituents include a methyl group, a halogen, and a nitro group. The nitro group is strongly deactivating. The halogen is weakly deactivating, and the methyl group is weakly activating. So by our first guideline, where we use the most activating group to determine the course of the EAS reaction, it is the methyl group that will control the outcome of this transformation. The methyl group directs ortho and para to itself. The position para to the methyl group is already occupied. There are two positions ortho to the methyl group that are open and available for reaction. However, one of them is between two substituents on the ring and is therefore too sterically hindered. This leaves us with one viable site for EAS reaction, and that is where chlorine resides in the product.